welcome back, everybody. Sorry I started going over the first couple problems without you guys at home. But here's numbers 2 and 3. Go ahead and pause if you need to. There we go. Here's 4, 5, and then through 9 as well down below. Check those. Again, I need the asymptote in the correct spot. I need the y-intercept in the correct spot, and I need it generally going in the correct direction. And there's number 6, 7, 8, 9 down on the bottom there. And then here's 10 and 11 as well. Yep.
I was going to ask how was your day yesterday?
Not because I didn't see you.
That was a boring response.
Sorry.
Yeah, that kind of hurt my feelings.
What did happen yesterday?
Baseball.
It was a nice warm day. We went outside. You posted Caleb on your phone? I did. Do you want to know what he was doing at that moment? I think he was looking at my Twitter. So I snapped the picture and posted it. Wait, why did you just post it? Was that right now? It's like, yeah, it was right now.
I'm actually fun.
All right, yes.
Can you go over to
10?
Yeah.
Yeah. Now, I would not do that same problem like that. I would actually do it in a little bit different way. I would say this. If I've got e to the 3 ln of x, well, that is equivalent to saying e to the ln of x to the third, right? And then e to the ln, well, remember, ln is log base e, so it's e to the log base e of x to the third, which that will cancel, leaving us just an x to the third. That make sense? Any other questions on the homework? Okay, well then let's get to our notes for today. Just the second day out of section 7.6. It's not really a full day of notes today. Really, section 7.6 is kind of like a day and a half lesson. Look, there's no back to the guy to this. So it's kind of, you should get some time to work on your homework. I'm not saying this is easier material. I'm just saying that it doesn't take a long time to talk through. Now, we learned yesterday that E is a constant. Well, I guess not yesterday, but whatever you learned it. E is a constant that occurs in the natural world. Okay? E is just basically a constant that occurs in the natural world. It occurs in a variety of different areas. Like what we'll learn today is it occurs when things naturally decay, in terms of like Halflife. Okay. Sometimes it occurs when things naturally grow. Okay. It occurs when, if I set a cup of coffee on the table and it's cooling, right? It's going to cool at a rate because, think about it. Like the air is always cooling it around it, right? Faster than every second, faster than every millisecond. It's constantly cooling the liquid inside there. So if something's constantly happening, it's probably going to have E within the equation. We looked at the PERT formula, the principal times e to the RT. That's that continuously compounding interest, right? It's always compounding the interest. It's not just taking it at some snapshots of time. It's always compounding the interest. So let's take a look at another example of that with Halflife. Now, have you guys studied Halflife before in science classes? No. It's been a minute, right? So the idea of Halflife is that after a given time, half of the substance remains, whatever it may be. If it's some sort of isotope or something like that, whatever. an element, whatever it is. After so many years, things will decay down and remain, it'll take a certain amount of time period for half of it to remain left over. That's why you get the name half-life, right? So the half-life of a substance is the time it takes for half of the substance to break down or to convert to something else during the process of decay. Now, is it like, okay, if I say the half-life is like 1 year, at the end of 1 year, does half the chunk like disintegrate? No, that's not how that works, right? It's not like a part, like half of it like just vanishes into thin air. It's naturally decaying. It's decomposing. You don't see the decomposition actually happen. You don't see the decay actually happen. It's just constantly happening over time. And then you can observe at that 1 year mark that half of it remains. Okay? It's not like it just laps off. It is naturally happening and it's constantly decaying. That's why E is within the formula. So here's our decay formula. N of T, the final amount remaining, is equal to N sub 0, or N naught, which means that's the initial amount, our beginning amount, because the number out front in front of the exponent is always your initial amount. Our initial amount times E, our natural base, to the negative K times T. Now, K is a decay constant, and it's going to be unique to each substance. We'll have to calculate what that is. And then T is the time. Now, time could be in years, time could be in minutes, time could be in hours, time could be in days. It all depends on the half-life. Whatever the half-life is given in, that's the time amounts. Okay? Now, you may be thinking like, okay, if I've got 50 grams of something, and I want to know how long it's going to take to decay down to 25 grams, well, that's one half-life cycle, right? So if I give you the half-life, well, you just need to calculate, oh, that's one half-life cycle. So that must mean, okay, whatever that half-life is, say it's 10 days or so. In 10 days, there's going to be 25 grams of it left. Well, in 20 days, there would be 12 and a half left. And then in another set of half-life, there would be, whatever 12 and a half divided by 2 is 6 1/4. Right? No, that's wrong. Whatever. But you could calculate it by hand like that, where you could figure out how many half-life cycles it's going to take to drop down. But you can use it. What if it's not nice? Like, what if I say I want to know when that 50-gram sample goes down to 30 grams? Well, then that's somewhere in between 0 and 1 half-life cycles, right? So we got to figure that out. That's what we'll be looking at today. All right, so we got plutonium-239 has a half-life of 24,110 years. How long does it take to decay down to 0.1 grams? I've got 1 gram sample, and I want to know how long it's going to take to decay down to 0.1 grams. All right, get my formula sheet here. All right, so my initial amount, what is my N sub 0? What is N now? 1, right? That's my initial amount. Okay. It's times e to the negative kt. Well, do we know k yet? Are we told the decay constant? No, we're not. What are we told? We're told the half-life. Now, t is not 24,110. Okay? T is going to be how long does it take? That's what we're looking for. T is going to be the unknown here. T is what we're going to try to solve for. Okay? Because that's the question being asked to us. How long does it take for this 1 gram sample to turn down into 0.1 gram? Think about it. In 24,110 years, this 1 gram is going to go to half a gram. And then in another set of half-life, 24,110 years, that half gram is going to go down to 0.25. It's going to go down to 0.125. And then somewhere in between there, it's going to reach that 0.1, but we don't know exactly because it's going to be a decimal value. So let's figure out when it's going to be. Now, the key here is we need to find what this decay constant actually is. Well, we could do that by using our formula. Look, if I know, if I have 1 gram, and it's going to take 24,110 years. If I plug that into our time value, what's my final amount after 24,110 years? What's my final amount after 24,110 years? 0.5. Right? We just talked about that. After 24,110 years, that 1 gram is going to decay down to a half a gram. Do I have an equation with only one variable in it? Yeah, because E is just a number. So let's solve that equation. We divide by the 1 to get it over to the other side, but really that's just saying like 0.5 is equal to e to the negative, and I'm going to bring the number out in front of k, negative 24,110k. All right, I've got a variable up within an exponent. How do I solve for that? How do I get a variable out of the exponent? What do I take? No. I take a logarithm, right? I take a logarithm. If you're trying to solve for a variable up in an exponent, I take a logarithm. So I say log base e, or what can we say instead of log base e? ln. ln of 0.5 is equal to negative 24,110. Okay. Log base e of 0.5 is equal to negative 24,110k. Can we calculate what that is? Yeah, we have an ln button on our calculator. But let's divide by negative 24,110 first. Let's see what that's going to be. Okay. So we go ln of 0.5. ln of 0.5 divided by negative 24,110. That's our decay constant. Really small number. Really small number. That's our k value. I'll do this. K equals that. Right? Everybody get that in their calculators? Now, don't lose track of that number. Keep that as the last thing that you calculated within your calculator so that when you go to do the next part, you don't have to estimate the value. You can use the exact value. Here's what I mean by that. We have not found what we're looking to find yet. We have not found our time. Because what I have to calculate is the fact that, well, I want to know when this 1 gram sample is going to go down to 0.1 gram. But I found k, right? This may look like an equation with 2 variables in it, but I'm just going to write k because I'm lazy, and I don't want to write 2.87 times 10 to the negative fifth. Okay, this is an equation with only 1 variable in it. I divide the 1 over to the other side, it would just give me a 0.1 times e to the negative kt. And then again, I have to solve for t, so I want to find the logarithm, log base e, or ln of 0.1 is equal to negative kt, and I would divide by negative k. ln of 0.1 divided by negative k is my t value. Do we know what k is? Yeah, so we can actually run the number here. ln of 0.1 divided by negative of my answer. See what I did there? I did not round that number. I'm just using it because it's the last answer stored within my calculator. So I'm getting my exact value. 80,091.69 years. 80,091.69 years. How did I know it was years? Because that was the half-life. That's the way the half-life is given. So what was the process? Well, the process was using the information given, using, What was the only thing I needed to determine the K constant? The decay constant, the K value. What was the only thing I needed? The half-life. That was the only thing I needed. That was it. I know I started with 1 gram, but did I really need that 1 gram? Say I actually started with, I don't know. Let me say this. What if I actually started with 50 grams? What if I started with 50 grams? What would it decay down to in 1 half-life cycle? 25. Say I started with 60 grams. That's a K value. What would it decay down to in 1 half-life? No matter what I start with, 1 half-life cycle is going to bring me down to half that amount. Watch what would happen for every time I would solve this. 25 over 50 is 0.5. 30 over 60 is 0.5. Look, it reduces down into that equation every single time, no matter how much we start with. So what you can really reduce that first part down into is the fact that 0.5 is equal to e to the negative k times your half-life. Right? That t value is going to be 1 half-life cycle when you have a 0.5. And you can even say this. If you want to go as far as to say ln of 0.5 is equal to negative k times your half-life. Because wouldn't that be the exact same way to solve that? Oh, it's not e anymore. Negative kt. Right? So you can even go so far as to say when you're trying to find your decay constant, it's ln of 1/2 is equal to negative k times your half-life. Let's do another example of that. Determine how long it will take for 650 milligrams of chromium 51, which has a half-life of about 28 days, to decay down to 200 milligrams. You know, I think it's somewhere between 1 and 2 half-life cycles. Because 1 half-life cycle is going to get me down to 325. And then 2 half-life cycles is going to get me lower than 200. So it's got to be somewhere in between 1 and 2 half-life cycles. That's the amount of days. I just don't know the exact amount. So let's find the exact amount. I know my N0, my N naught is going to be 650. My K value, I don't know yet. I can find that, but my T, look, how long is it going to take? That's the unknown. So let's find our decay constant. We just got done saying that this is going to reduce down into 0.5 is equal to E times negative K times my half-life, 28. Change it into a logarithm. ln of 1/2 is equal to negative 28 times k. I just brought the 28 in front of the k. Remember, log base e of 0.5 is negative k times 28. I'm just spiraling it back. All right, so we divide by negative 28, and that's going to get me our k value. Let's see what number that is. ln of 0.5 divided by negative 28. Okay, that's a little bit more manageable number. 0.248. We'll say 0.0248. 0.0248. So that's our k value. I won't be lazy this time. 0.0248. So now I can answer my question. I can say, well, if I'm starting with 625, or sorry, 650, excuse me, and I want to know how that's going to decay, how long it's going to decay down to 200, that's my final amount, E times negative K, negative 0.0248 T. And that's the equation I'm going to solve. So on the left side is just prep work to solve the problem. All right, so we divide over the 650. We get our division out of the way, multiplication and division out of the way. I could leave that as a unsimplified fraction. I really don't care to simplify that. We're just going to plug it in our calculator in a second. E to the negative 0.0248 t. And then we take log base E of this is equal to the exponent. So ln of 200 over 650 is equal to negative 0.0248 times t. And we divide by the negative k value. Write that out. ln of 200 over 650 divided by negative 0.0248. That's going to be our time. Now, I am not going to round that number. I'm going to plug this in all at once. I'm going to say ln of 200 over 650 divided by negative answer. And there's how long it's going to take, 47.61 days. In science class, a lot of the times what you do is you just figure out how many half-life cycles it's going to take. And usually it works out to be a nice clean number. Or you can kind of estimate where it's going to be. Now we can get it down to the decimal. We can get it down to be a little bit more exact using E. All right, so there's our half-life application. The last thing I want to do with you guys today is work a little bit more with some algebraic examples using E. Like, for example, this one here. Because, again, I think a lot of the times you guys lose sight of the fact that, again, E is just a number, and E is just an ln is just a logarithm that you can use the properties that we've learned the exact same way with E as we had done with log base, well, anything else. So if I've got ln of 5 plus ln of x is equal to 1, how would I solve that? How could I reduce that left side of that equation? Multiply, right? Addition means to multiply. So I can say ln of 5x is 1. Right? Addition of the logarithms, as long as they have the same base, and they do, they're both natural logs. So ln of 5x is equal to 1. And now I can say, well, if I want to solve for something inside the logarithm, let's change it from logarithmic form into exponential form. So I could say e to the first power is equal to 5x. Spiral it. Log base e of 1 is 5x. And now we just divide by 5. So if you wanted the exact answer, you could say e over 5 is equal to x. But let's figure out what the decimal is. ln of 5, or sorry, not ln of 5, e over 5 is 0.544. There's my answer. So let's take a look at the other one that we have down below. Any questions on that one? Good there? Okay, let's take a look at the other one that we have. ln of 10 plus ln of x squared is equal to 10. Well, again, addition means to multiply. So I can say ln of 10x squared is 10. All right, well, change it from logarithmic form into exponential. E to the 10th is equal to 10x squared. And now I can just evaluate. Divide by 10. So e to the 10th over 10 is equal to x squared. And I can just take the square root of that. The square root, and I would have to say plus or minus the square root of e to the 10th over 10. let's figure out what that is. I'm going to take e to the 10th, divide that by 10, and then I'm going to take the square root of that, and I'm going to get 46.93. So x is equal to plus or minus 46.93. Now, I'm making a point to say plus or minus. Can I keep both answers? Yes. Look at your original problem. What does x do? It gets squared. X gets squared, right? So what's going to happen before I evaluate the log? It's going to turn positive. And since it's going to turn positive before you evaluate the log, well then yeah, the negative answer will still work. Because it would be negative 46.93 squared, which would turn positive, then I can evaluate the log, it's still within my domain. I'm not technically evaluating the log of a negative number. Wanted to give you one where a negative answer still exists in this case. So yeah, my true answer is plus or minus 46.93, and I can keep both answers. Cool. All right. Hope we had a good time with our notes today. I'll see you guys later.